So we're going to start looking at magnets. And magnets were really first discovered because people started noticing that certain types of rocks seem to attract to each other or repel, depending on how they did it. There's some sort of force between the rocks. And generally these materials were either iron or nickel, or really just a very few number of elements that seem to attract and repel. And it was really exciting because then explorers noticed that, oh, if I drop this magnet and just float it and let it be loose, it actually tends to point towards the north. And so it became very useful. Everyone started using it in ships and so forth to tell where they are. And it became something that was really, really curious and elicited sort of a lot of early research as far as like what we might call scientists now, looking into what exactly was happening with the magnets. So for our purposes, I'm going to put this magnet up here. And if I bring in another magnet, in this case, I bring in a little compass, and if I put the compass next to it, the compass is going to tend to point towards or away from it. And it's because the compass itself, it has a very, very tiny little magnet in it itself, is a magnet itself, and so it either attracts or repels. So for example, if I stick the compass right there, it's absolutely attracted. If I stick it here, the pointer, the little point on the compass, points away. In fact, I can take the compass and I can put it all around the magnet. If I follow which way the arrows face, I'm going to get something that looks very, very similar to our electric field lines. And in fact, these are called magnetic field lines. The magnetic field lines are pointing in the same direction that my compass points. In other words, they point in the direction that the north side of a compass would point. But in magnets, the opposites attract, so that means that this north side here is being attracted towards the south side of this particular compass, south-north. This compass points away from the north and towards the south. This can be very, very confusing when we start looking at the Earth. On the Earth, if I were to put a compass on here, the compass points northward, right? What we have defined as towards the North Pole, or the north direction on the surface of the Earth. But that means that this north end of the compass is being attracted up towards the north, meaning that what we call the north magnetic pole on the Earth is actually the south end of a magnet. North side of the Earth, south end of the Earth magnet. The Earth is a magnet because the Earth is made up of a whole bunch of iron and nickel, two of the most magnetic elements. And we can talk more about how this affects how we live on Earth later on. For today, let's just look at what exactly these effects are and how we might evaluate them. Most importantly, how do they relate to electricity? If I have a coil of wire and I connect it to a battery like so, I have a lot of current flowing through this wire. If I were to stick my compass in the middle, suddenly my compass is no longer just pointing north. It's actually affected by this current moving through the wire. If I take a lot of coils of wire and I stick the compass in near these coils of wire, the compass is actually affected by the current. So if I attach a current and the current flows through these coils, it creates a magnetic field. Moving current creates magnetism. Moving electrons create magnetism. Let's say for a moment that I have a wire going this way. The current goes that way, meaning that the electrons themselves are actually moving downward, but we say the current is moving up. So this is the positive direction of the current. I get a particular magnetic field, and if I were to take a compass here and stick the compass right on this side, I would get lines that would point outward, or point out from the board. And then if I came over to this side, I see that the compass pointed into the board. In other words, there's circles of magnetic field lines going around this particular wire. Now this could get confusing in real life, so we actually have a simplification or a rule that we can use to determine which way the field lines are going. I take my thumb and I put my thumb in the direction of the current. And this is the thumb of my right hand. It only works with my right hand. I take the thumb of my right hand, I point it in the direction of the current, And notice my fingers are curling here. If I imagine a wire in between, notice my fingers would curl around it. That's the direction of the magnetic field. In other words, the magnetic field is coming out and then coming in on the other side, like so. This is called the right-hand rule for determining the magnetic field due to a current. But it's only the first of two right-hand rules I'm going to show you. So looking at this, now let me talk about the second right-hand rule. Not only does the current itself create a magnetic field, but if the current is moving through a magnetic field, the current is going to experience a force. For example, let's say I have a wire. Here's a wire, and I put that wire in a magnetic field. The magnetic field, let's say, points up in this direction. How might I actually have that in a physical situation? Imagine this, lots of magnets, wire. This right here is a wire. If I were to run current through the wire, it would be this situation, current flowing, magnetic field upward. The force that this particular wire is going to feel is in a very particular direction, and I can determine that direction using my second right-hand rule. To do that, I take my hand, so take your right hand, shake it out a little bit. Make sure it's your right hand. Make sure it's your right hand. Put your hand like this, fold these three fingers in, and notice that now I have my thumb pointing one way, my forefinger pointing another way, and these three fingers pointing another way. They're all at right angles to each other. My finger is going to point in the direction of the current, which in this case goes this way. I have to turn around. These three fingers point in the direction of magnetic field. It's sort of like they form a B. So they point in the direction of magnetic field, and my thumb points in the direction of the force on this wire. So this wire is going to be pushed outward. Fingers, direction of current. Three fingers is direction of magnetic field. Thumb is direction of force. So looking at this, I want to say the force is coming outward, but I now have three dimensions. I only have a two-dimensional surface. What we often do to draw arrows that come in and out of the board is like this. I can draw a circle with a little point. It's as if you're looking at an arrow coming right at you. So this is the direction of my force. Force, magnetic field, abbreviated with a B, and current. So the force here is coming out of the board. I get the same type of situation if instead of current, I just have an electron or a proton. I'm going to use a proton, since a proton will be moving in the same direction as a current. Let's say I have a proton moving like this, in this direction. So, proton, positive, and it has a velocity in this direction, so this is its velocity. In other words, this is the direction of the current. I'm going to use the same magnetic field, pointing upward. What's going to be now the direction of force on this proton? So again, I take my right hand, fold down these three fingers. I want this finger going in the direction of the current, or the direction of the velocity for the proton. My thumb is now facing the direction of, oh, it doesn't work. I take my fingers, I actually have to turn my hand so that these three fingers face in the direction of the magnetic field, and then my thumb is going to point into the board. So the force on this particular proton is going to be into the board, and to represent that, I can again draw little circles, and then imagine I'm looking at the tail feathers of an arrow. So it's a little circle with crosses. That's the force into the board on this particular proton. Now, if we want to actually evaluate some numbers here, I can say the force on a particular current, I can say that force is probably going to be proportional to, well, the strength of the current, the amount of it in there, the amount of wire in there, so the length of it, the magnetic field, and also the angle. What really counts is sort of that the orthogonality In other words, how much of a right angle it is. So if they're all at right angles, it might just be like this, but if not, then we're going to want to do sine theta, where theta is the angle between the current and the magnetic field. So the force is probably proportional, well, it has been determined to be directly proportional to each one of these. And so we could just stick a constant in here. However, what physicists did was they said, well, we haven't actually defined magnetic field yet. So let's just make this the definition of magnetic field. So we can set these equal without any constant. I, L, B, sine theta. And if they're at exactly right angles, then you can ignore this part and say it's just force equals current times length times the magnetic field. Using the same equation, I can quickly figure out, well, what would be the force on a proton, for example. Notice that current is just charge per change in time, times length, times b, times sine theta. If I move this change in time underneath the length, then I get q, length over change in time, b sine theta. But the length, the distance that that proton has moved divided by the change in time, is just the proton's velocity. So force equals charge times velocity times the strength of the magnetic field. With sine theta, it's not exactly a 90-degree angle. This should be enough to get you started on all the work we're going to do in Chapter 20 and the worksheet that I gave you. Good luck.